Hello, my name is John Mount. I'm a principal consultant with a data science training and consulting company called WinVector LLC, and I'm here to talk about solving forecasting problems in R and Python, which is a lot about picking the right package to do it. And there's a number of excellent packages both in R and in Python. So the motivation is that many data scientists, myself included, think that time series or forecasting methods are very much under-taught topics. And the reason is they're highly technical and there's a number of hidden gotchas that are not in traditional predictive modeling. However, they're underserved because they're really high value. They can move you closer to money and decisions in businesses. And so basically, they're very much something we should do more of. And I want to set us all up to be well-versed to do that. So we're going to start with a little motivation. We'll define our terms. What is time series work or forecasting work? What are the major families of methodologies and how do you navigate through that? Actually, the literature is quite deep, which can be both good and bad. We'll set up an example problem, which would just be the usual mathematician's scummy little problem of fitting sine x. And then we'll show a really interesting solution to that problem using Stan, which is a Bayesian reasoning package that has interfaces both to R and to Python. And we'll define what Stan is and go over some of the consequences of the results. We'll also name a number of packages that can be used directly on these time series problems. So what is time series forecasting? I'm going to give a slightly heterodox view, and it's basically it's taking data like this, where the x-axis is time, and in time series forecasting, time is often a synonym for date, and the y-axis is a single regressor or value we're trying to measure over time. The left portion of this graph with the dots and lines are the values of this variable over time. The lines are just there for legibility. The dots are the observed values. So this is a time series measured at discrete regular times. There are other kinds, such as continuous time. And then the goal of time series forecasting is to taking all the data on the left, produce the green cloud on the right. The center line is the predicted value for that y value in the future, and then the spread region or shading is the uncertainty that the model has in that prediction. Now, a time series or forecasting result is good if, when the future data arrives, it happens to be near the predictions. So what we've done now is we've added in the dots, which are the future. Now, of course, in time series systems, the way we simulate the future is we hold out data based on a date. So we say every time past time tick 980 was, quote, the future, even though we were already at time 1000. The business applications of this are quite diverse. They involve things like predicting future demand of online sales, such as parking or a restaurant, predicting future prices, such as expenses or stocks, predicting revenue, which can allow revenue planning. There's a little bit of a Cassandra paradox there that sometimes you're predicting a future you're trying to avoid, or even predicting physical systems such as tides or weather that impact business decisions. This picture here is Lord Kelvin's tide predicting machine, where you literally turn the crank. Now that we're in and happy, let's have a little demotivation. This is an announcement by the Facebook group when they released Profit, which is an excellent forecasting system specialized to dates and business purposes. And I agree with what they've said, that most of the systems that do time series forecasting, they're so good you can't ignore them, but they're so technical you're unlikely to use them correctly in the first few encounters. So let's also get to what I consider a neglected topic, as an example of where these things go a bit too technical is the following ARIMA example. ARIMA being a term I'll define in a bit, one of the most popular time series forecasting methods and sometimes wrongly thought of as the only one. This ARIMA system says you have to go through several pages of diagnostics and prep and checking before you're rightly using the system. So if you skip any of these, you're in a state of sin. This one happens to be an R package. I can tell by the arrow assignment. And after all that, even in their own examples, they then show a fit in the notation we've shown, where you show the past and the future, which actually a lot of time series people avoid even making this plot. And the plot gives up immediately. It's a degenerate fit. The past is the black line in this plot, which is jaggedly going up and down. The future is the straight line with the blue uncertainty intervals. And this model is saying there's no reason to believe the world goes up or down, and I'm very uncertain even about that. Now, of course, it could be that this is pure noise and it's very hard to predict, but there's cheaper ways to fail than going for all of this structure and then doing this. Also, it's usually not called out that this is what a degenerate or failed fit looks like. The other problem beyond technicality is frankly the field's complete hatred of external regressors. Even the name is a thing. These are basically the explanatory variables in predictive modeling. So in addition to saying the time series evolves forward where the future is a function of the near past, which is the autoregressive part of the word arima. The A is for autoregressive, function of self. We often want to introduce external regressors. In fact, if we come from a predictive modeling background, we always want to introduce external regressors. They're the variables. The addiction of external regressors to ARIMA changes ARIMA to RMAX and SARMAX. Or RMAX, depending whether you have the I or not, which is allowed. Now, the problem is external regressors are not quite as easy to deal with as you'd think, and most of the packages don't define clearly what they do with them, which is very odd. And Professor Hindman has really excellent packages on this and really excellent writing on why that is so obscure. So let's go through families of methodologies. I break it down into 3 to 4 major families. The first family is the ARIMA family. And the ARIMA is an acronym standing for Autoregressive Integrated Moving Average. Autoregressive means the future is a function of similar things, i.e. the past. And it's really technical. Then there's the brute force methods. These methods were kind of spat upon for quite a while, but then became very popular in the neural net community. And I think in addition to the neural network being quite good, just going for a brute force method is a pretty good idea, though it has some consequences. Then there's the decompositional attributional methods, which are related to the hidden state inference. Profit is an example of that, and Stan is an example of the fourth category. ARIMA is the, as promised, autoregressive integrated moving average. And it's basically says the world is a set of linear equations. And for instance, this model is just saying y at time t is probably about 1.975 y at t minus 1 minus y at t minus 2. And if you want to predict 2 steps forward, you just iterate. You use your prediction and plug it in as if it's an observation. So if you want to go 5 ticks out, you iterate this equation 5 times. Now the time series fitting is finding these coefficients 1.975 and minus 1. Now, if you have any experience with iterated formulas, you know they're very unstable and hard to fit. So it's a somewhat unsafe way of working. Also, ARIMA uses this very neat or nifty differential operator or difference operator notation. And that can be actually quite hard to read. And the most well understood RMAX version, or how to get in the external regressors, which we would just call explanatory variables, is called regression with ARIMA residuals. It often goes under the RMAX flag, but you don't know what you have when you have an RMAX. When you have regression with ARIMA residuals, there's an ARIMA process that you don't observe, and what you observe is noised up by these external regressors, which we'll go back to when we do some more equations. The definitions of what external regressor does are fairly inconsistent. For instance, in the pi flux time series package, the external regressors are not applied late in the system. They're applied in the autoregressive equation, and you can't really read equations. You just sort of hunt through them and see who has subscripts, who has the difference operators, and who does not. And from that sort of inspection, on the very right side of this equation, you can see that the external regressors are part of the autoregressive process and not just part of the observance of such. So they're what I would call durable external regressors. So this would be stuff for studying policy, like introduction of seatbelt laws or catalytic converters. So econometrics might prefer this system, whereas sales, we'd prefer regression with ARIMA residuals. This will make clearer when we get to our main equation system. The other families of methods are the so-called brute force methods. Now, as I said in ARIMA, to predict 5 days out, you predict 1 day out, plug in that as if it was an actual observation of the future, and iterate to get 2 days out, then iterate to get 3 days out. The brute force method says actually during your model fitting, just fit a family or pencil of models. So fit one that predicts 1 day out, fit another that predicts 2 days out, fit another that predicts 3 days out. And when somebody asks you to predict k days out, just get the kth model, plug in what you know, and give that answer. This works actually quite well. And it is usually the pre-processing that is done whenever deep learning or a neural net is applied to solve time series problems. That they tend to do this because the feedback into a linear function is already dangerous. Feeding back into a neural net would be incredibly nasty. The decomposition or attribution family of methods, which is again what Profit does and also what Bayesian systems do, is you write down the past, which is these dots indexed by date, as a linear combination of unlabeled unknown subsystems. So you go, these dots are some combination of a trend, some combination of a weekly effect, some combination of a yearly effect or a seasonality, and some combination of an external regressor, which again those are those four things I've said are the 4 panels there. And the external regressor is a variable that's either on or off, and it contributes to this time series. So it has this jaggy thing. It itself is unpredictable, but we assume it's something we know in the future. For instance, it could be whether there's an event near our movie theater or near our restaurant, because we can buy that data from suppliers. Now, the idea is if you can write the past as a combination of these smooth or well-explained systems, each of which can be extended into the future, then the same combination of the future would then predict the future. The way this works, since this is all unlabeled, the training data, you don't know in your restaurant what fraction of the people are coming due to the fact it's January, what fraction of the people are coming due to the fact it's Tuesday, is called hidden state inference. And for this, we have to use a Bayesian method. And it's fairly non-intuitive, but it doesn't need to be intuitive because it's correct. The Bayesian statement is, if there are model parameters that affect how the data is generated, then observing the data affects the plausible distribution or value of those parameters. So, and how it affects that is given by an inference formula that is correct, though nasty. It's you have to basically compute this ratio of integrals, and these integrals can be intractable. However, a numeric system such as Stan can estimate them for you, and you don't have to write down the integrals. You write down the problem. Stan knows it implies solving these equations and then solves them for you. So let's go to our example problem, which I think is a tool to make this a lot clearer. We're going to be modeling how many people visit a restaurant every day. We want to improve the prediction by bringing in external information. We're going to break the rule of the REMA systems and actually explain what how the external information is used. We assume we have 2 types of external regressors. One are transient regressors. That would be, say, things that bring in customers that aren't going to return. So they're not part of the so-called time series system or the part of the autocorrelative system that somebody comes in to eat because they were at a movie Monday night, they're probably not coming back Tuesday night. So these are the transient or the Groupon style things. There's also the durable external regressors. Did we get a good food review? Did we lower prices? Those we think, they affect Monday and they also affect Tuesday and so on. So one can play some tricks about integrating to try to get one type of external regressor to imitate the other. But my whole point is most of these systems don't even document how they use external regressors, so you don't even know which way they are. And none of them ever have given you control of 2. And I think this is really important. As equations, we're modeling this restaurant as 2 types of external regressors, which is a little easier to explain as saying there's 2 types of guests at the restaurant. There's loyal guests, and they're part of the autoregressive process. That the number of loyal guests on a given date is some linear function of the loyal guests on some previous dates, plus an external or durable external regressor, such as restaurant reviews. Then there's the transient guests, which are just some function of external regressors. You notice the loyal guests have loyal guests on both sides of the equation. The transient guests have it only on the left side of the equation. That how many transient guests are here Monday doesn't affect how many transient guests appear Tuesday. Now, both of these are called unobserved variables. Unless we go into the restaurant and ask every guest whether they're loyal or transient, we don't know if we have 10 guests in the restaurant, whether it's 7 loyal, 3 transient, or 5 loyal, 5 transient. So we only observe the sum, which is total guests. And this is the problem. In most hard statistical problems are this sort of data censorship, that there's an underlying system that evolves in a reasonable or rational way, but we don't observe it. We observe some function or summary of it. So, can a standard package solve this? Here I've just eliminated transient guests by substituting into normal loyal total guests. And if we force B review equals 0, this is regression with ARIMA residuals. That regression with ARIMA residuals means there's an unobserved process that moves smoothly or auto-correlated over time, but you don't observe it. You observe it plus some extra system. If we set B events equals 0, this is the sort of system that PyFlux was solving, where there's a durable policy change, such as introduction of tariffs, seatbelt laws, or catalytic converters. So you really have to know, is the package designed to solve the sort of problems you want to solve? Let's solve the problem I want to solve is just artificial example, which is just sine x. I apologize. It's a trivial example, but it's about the most complicated one where I can really explain what's going on. And again, that's part of delegating things to powerful packages. They do a good job, but you yourself don't know all the specific reasons they do a good job. And this data is subject to 2 external regressors, 1 durable, 1 transient. And it causes certain things like the observation, and plus unexplainable noise. And then the held out data is the time ticks from 900 forward. And these are what those are. Now, we're going to just skip ahead to the result. All code and data and every package I've mentioned is shared. Here's the stand result. This is really neat, in my opinion. The input data is just the top left panel. The dots of what happened in the past indexed by time. How many guests were in the restaurant every day. And again, it's a false example. Every other panel, other than the top left panel, is the stand result. For instance, the middle left panel is the estimated fraction of the customers that were loyal or autoregressive. The bottom left panel is the estimated count of customers that were transient, brought in from an known external event, such as a known scheduled movie in the neighborhood. Even this decomposition of the past, and again, it's an inference. We don't know this is what they are. This is what the model thinks they are. Even this decomposition, you can drive your business on that. That you can say, what fraction of my customers are loyal versus transient? And do I want to adjust that? Then the right side panels are all the projections into the future. And the autoregressive, our past depends on self thing, our future depends on self thing, is the middle panel, and it evolves smoothly forward. The kink in the left of the panel is where one of the durable variables changed. The future of the external events panels, we know what those external events are because we subscribed to something that tells them us, and this is saying, well, in customers, how many customers are expected to arrive each date due to these external stimuli, such as a movie near your restaurant. And then finally, the top right panel is the sum of those 2 panels. And I've put in the dots that are the held out future, which are not seen during model fitting and also not seen during model evaluation. The model stops all training at time 980 and stops all sensing at time 980. So when it's predicting at time 990, that's 10 steps into its future. And it's a really high quality fit. We can do the usual things such as an R squared. Be aware that this is combining predictions that are 1 tick out with predictions that are 2 ticks out. Never accept this graph where it's only 1 tick out. I call that sort of the liar's graph, and that's in finance a lot. So this scatter plot often has a high correlation just because this underlying system has a high variance, and that using the most recent time gets a high R squared. So you have to not allow quantitative evaluations only on one tick out models. Also from the Stan system, you get estimates of the coefficients. For instance, the durable and transient coefficients were in the simulated data 14.2 and 16.1 respectively. And these graphs are the distribution, or posterior distribution of the estimate. And it's saying, it thinks that the one that's 14.2 is around 13.5, and it thinks the one that's 16.1 is around 16. Now, we can't say this is biased because this is only one estimate distributionally. So it's only if it run again and again was always under or always over, we talk about bias, but this is its posterior distribution of plausible values for those things. And again, you may not even need to call model predict. Knowing these coefficients may help you set policy. If the transient linkage is high, you spend more on advertising. If the durable linkage is high, you spend more on marketing. So how did we solve that? We translated the equations that we had written in LaTeX into Stan. And it's just two equations, that y durable, or the autoregressive, or y auto, is just a function of some other y auto versions, and the y observed is y auto plus the transient variables that we don't know. And all of these betas or b's are the coefficients to be inferred. So Stan is told the historic data, it's told this causal or equation form, and then it says, well, then what are the plausible values, or distributions of the plausible values, those unknown coefficients. And then it also infers the future, as to the future is just yet another parameter, just like the betas. What we get back from Stan are 4,000 trajectories. Each trajectory is a different simulation of what the unknown, or a sampling of what the unknown parameters and future are. So each row is a different projection or inference, and each column is a variable. And many of the variables are internal, like LP underbar, but many of them are what we want to talk about, such as Y990, which is the estimated or inferred number of visitors at time 990, and also these betas. Our overall thesis is that in business forecasting, the ability to implement and document the actual business structure beats technique in forecasting. And the Stan and profit paths really allow you to specify much more directly what you are up to, including external variables. Now, if you're going to use a more standard package in R, that would be Fable or Forecast. And in Python, it would be stats models, the time series system and stats models. And it might be PyFlux, but for me, that sort of lashed into the NumPy of my installation in a weird way, and I wasn't quite happy with it. But basically, the standard ways are usually an ARIMA-style method, such as forecasts or Fable in R, or the forecasting in Python's stats models. And then the non-standard ways would be Profit and Stan. And both Profit and Stan are much more problem specification oriented, and that gives you quite the advantage. And the other thing about time series is you really need to work hard to keep the explainability up. That quality of prediction is not a sufficient metric for whether the model has high utility for your business. So thank you. All packages mentioned and the exact same problem solved with each and every package mentioned are here. And basically, most of the packages get a high-quality solution, but do not get the same high-quality solution that the Stan got, because none of them can represent that we have two types of external variables. And the Stan solution is there also, so we've worked it with about 6 or 8 different packages in R and Python, just to show the sort of breadth of what's available. And thank you very much for your time.